Welcome to the Explainer. Today we're going to tackle one of those things that seems small but trips up almost everyone diving into data science with Python. What is going on with NumPy array shapes? You know, it seems simple, but it gets even experienced developers all twisted up.
So let's just jump right in with a classic puzzle that I guarantee you've seen before. A developer runs some code, gets two results, and they look almost the same, but they're not. So what's happening here? Let's clear this up right now.
Okay, on one side, you've got .size, and it gives you 90. Simple, right? That's just the total number of items in the array. But then you look at .shape, and you get 90, comma. What is that weird trailing comma doing there? Well, that's the whole secret. That comma tells you you're looking at a tuple, not just a number. And that means you have a one-dimensional array. Think of it as a single row. That's 90 elements long.
To really crack this code, we just need to get three little definitions straight. Once you get these three attributes, I promise, you've got the foundation for pretty much everything else in NumPy.
First up, ndim. This is just a simple number that tells you how many dimensions your array has. NumPy likes to call them axes. So if you've got a flat list of numbers, your ndim is 1. If it looks like a table with rows and columns, ndim is 2. A stack of those tables, yep, that's 3. Super simple.
Next, we have size. We've already seen this one. It's the easiest of all. It's just the total number of elements, period. It doesn't care about rows or columns or any of that structure. A 3x4 table? The size is 12. It just gives you the grand total.
And now for the star of the show, shape. It's a tuple of numbers that lays out the size of each dimension. And here's the real key. The number of items in the shape tuple is always the same as your ndim. So a 2D array will have a shape with two numbers in it, like number of rows, number of columns. This is the one that really defines the array's structure.
Okay, so theory is one thing, but how do you figure out an array's shape just by looking at a bunch of code and brackets? All right, I'm going to show you a super practical method that works every single time, I promise. No more guessing.
We're going to call it the nesting doll method. You know, like those Russian dolls where there's a smaller one inside a bigger one. All you have to do is think of the array's square brackets in the same way. You just start from the outside and count your way in. Here's exactly how it works. First, find the outermost pair of square brackets. Just count how many items or containers are inside it. That number, that's the very first number of your shape. Then you dive into one of those containers and do it again. Count what's inside it. That's your second number. You just keep doing that until you're down to the individual numbers.
Ready to put this to work? This is where the theory actually becomes a skill. We're going to take our method and apply it to a couple of examples that, honestly, leave a lot of people scratching their heads. This is where it's going to click for you.
Check this out. Someone posted this online totally stumped. At first glance, yeah, 1, 2, 3, 4 looks like a complete mess of brackets, doesn't it? But using our nesting doll method, we can decode this no problem.
Okay, let's do it together. Step 1. Look at the outermost bracket. How many things are inside? We see two main blocks, right? The curly bracket 1, curly bracket 2 block, and the curly bracket 3, curly bracket 4 block. So our first number is 2. Step 2. Now let's just look inside that first block. How many items are in there? 2 lists, 1 and 2. So our second number is also 2. And finally, step 3. Let's go inside one of those lists, like 1. How many elements are in there? Just 1. So our last number is 1. And there you have it. The shape is 2, 2, 1. See? Not so scary.
Now for another classic point of confusion. On the left, you've got a simple 1D array, a vector. Its shape is 5, with the comma. But on the right, every single number is wrapped in its own set of brackets. If we use our method, we count 5 containers on the outside and then 1 element inside each of those. The shape is 5, 1. And this is huge. The one on the left is a 1D vector. The one on the right is a 2D array. It's a column with 5 rows and 1 column. Those extra brackets make all the difference.
So counting brackets is the how. That's the practical skill. But now let's get to the why. Let's actually try to visualize what these shapes mean in our heads. This is the part that really makes it all make sense.
Let's map these to something real.
A 1D array? That's just a line, a vector of numbers. Easy. A 2D array? Think of it like a flat sheet of paper, or a spreadsheet. It's a matrix. It's got rows and columns. This is how we store tables of data.
So, what on earth is a 3D array? It's just a stack of those 2D sheets of paper. That's it. Let's go back to that 2-2-1 array we solved. The very first number in the shape, the 2, tells you how many sheets are in your stack. And the rest of the shape, the 2-1, tells you that each sheet is a 2-by-1 matrix. That first number is always how deep your stack is.
Okay, so why do we just spend all this time obsessing over brackets and tuples and shapes? Why is this so critical? Well, because getting the shape right is literally the key to unlocking almost everything else you're going to do in data science.
I mean, everything depends on it. You want to multiply two matrices? It literally will not work if the shapes aren't compatible. You need to get your data ready for a machine learning model. You have to reshape it first. And hey, if you ever do image processing, guess what? An image is just a big 3D array of pixel values. If you get the shape wrong, nothing else you do is going to work.
So look, mastering shape is step 1, and it's a huge one. But the real magic, the thing that feels like a superpower, is when you see how NumPy uses this shape info to do math on arrays of completely different shapes. It's a concept called broadcasting, and, well, that's a story for another explainer.